Imagine sitting in the passenger seat of a self-driving car navigating a winding mountain road. If the camera sees the road curve sharply to the left, the car can't just jerk the wheel 90 degrees. So how does it make thousands of tiny, split-second adjustments to the steering without crashing? To stay safe, the car must measure exactly how fast that curve is changing. It relies on calculus, the mathematics of change and motion. Calculus lets the computer ask, how is my situation shifting right now, and what exact tiny movement do I need to make to stay safe? This split screen shows the connection. On the left is our car, and on the right is the mathematical surface it is actually navigating. To get that dot safely to the bottom of the valley, which represents zero error, the car uses three core concepts: functions, gradients, and the chain rule. Over the next few minutes, we will define these three concepts. Then we'll calculate a numerical gradient and solve a multivariable gradient, exactly like an artificial intelligence. Mastering these calculations reveals the mechanics that allow a model to optimize its parameters. This is the process by which a system translates mistakes into measurable improvements. Step 1 is the function. In machine learning, a function is a prediction machine. It takes an input, like the road ahead, and gives an output, like a steering angle. Think of it as the mathematical landscape we are driving on. In this equation, W for weight and B for bias are the adjustable values the car tunes to stay centered. Step 2 is the partial derivative. Because a car has multiple variables, steering, braking, acceleration, we need a way to test them individually. A partial derivative acts as a compass. It tells the car how the error changes if we tweak just the steering wheel by 1 degree, while keeping the brakes and gas perfectly constant. When we group all of those individual partial derivatives together into a single vector, we get the gradient. If a single partial derivative tells you the slope in one specific direction, the gradient points you toward the steepest path down the hill to minimize your total error. Finally, we have the chain rule. When the car makes a mistake, the chain rule traces that error backward through the entire sequence of steps, from the motor turning the wheel, back to the computer calculating distance, back to the original camera data, to find exactly which setting requires adjustment. Together, the function maps the landscape, the gradient points down the hill, and the chain rule traces which internal settings must update to get you there safely. Now that we know what a gradient does, let's calculate one. When a machine learning model faces an equation too complex for standard calculus formulas, it uses a numerical gradient calculation to approximate the slope. This is the numerical slope formula. To see how it works, we'll use a simple baseline equation. F of x equals x squared. We'll start at an input where x is 3, and we'll use h to represent a tiny step forward. Let's make h exactly 0.01. First, we calculate our baseline. If we plug 3 into our x squared equation, 3 squared gives us an output of 9. Next, we add our tiny 0.01 step to x, bringing our input to 3.01. If we plug that nudged value into our equation, 3.01 squared equals 9.0601. We have our two outputs. Now we just plug them back into our original formula. We take our nudged output, subtract our baseline output of 9, and divide that difference by our tiny step size. When we subtract 9 from 9.0601, we get 0.0601. Divide that by 0.01, and we get a final slope of 6.01. Using the power rule, the exact derivative of x squared is 2 times x. At x equals 3, that gives us exactly 6. Our estimate of 6.01 is incredibly close to that true value. By nudging a variable by a tiny amount and measuring the difference, computers can programmatically determine the slope of their error curve. They do not need to solve symbolic calculus by hand. They just take a tiny step and measure the change. Finding the slope is only half the job. To learn, the model uses that slope to update its internal parameters and fix the error. This is the weight update rule. The critical detail here is the minus sign. To move toward the bottom of the valley, where the error is lowest, the model must subtract the gradient from its current position. This process is known as gradient descent. Let's test this. If we calculate a gradient of 10, we don't just subtract 10 directly. We multiply it by a small factor called the learning rate, represented by the Greek letter eta. If our learning rate is 0.01, we multiply that by 10, giving us a step size of 0.1. We subtract that 0.1 from our old weight. Scaling the gradient down ensures the model takes a controlled step down the hill. Without it, the model might take a massive leap and overshoot the bottom of the valley entirely. Real models have more than one variable, so let's solve a multivariable gradient. Our equation is f of x and y equals 3x squared plus 4y plus 5. We want to find the gradient at the coordinates where x is 1 and y is 2. To find our gradient vector, we need two separate partial derivatives. Let's start with x. We treat every other variable as a static number. The derivative of 4y becomes 0. The derivative of 5 is 0. We apply the power rule to 3x squared, leaving us with a partial derivative of 6x. Now we do the same for y. This time, the 3x squared becomes 0, and the 5 remains 0. The derivative of 4y is just the coefficient, so our partial derivative for y is exactly 4. We place those two partial derivatives side by side to build our complete gradient vector. The result is an array containing 6x and 4. Finally, we plug in our standing coordinates. Our x value is 1, so 6 times 1 is 6. The y component is a constant 4. Our resulting gradient at point 1, 2 is exactly 6, 4. That final vector is a specific set of directions. It tells the model that to increase its output fastest from its current position, it must move 6 units in the x direction for every 4 units it moves in the y direction. To decrease the error, it simply moves in the opposite direction. We have now constructed the complete learning loop. The model makes a prediction through a function, measures the slope of its mistakes using gradients, traces those mistakes to their source using the chain rule, and subtracts that gradient to improve. You've seen exactly how this math plays out. We used a tiny 0.01 step to approximate a numerical gradient of 6.01, demonstrating how computers probe their error landscape. You also solved a true multivariable equation. By computing partial derivatives, we derived an exact gradient vector of 6, 4, isolating the specific directions required to navigate the model's internal topography. You now have a concrete understanding of the optimization process used by modern AI. You have calculated how a machine measures change and updates its internal settings to minimize error. With these fundamentals, you are ready to apply these logic patterns in your own code.